First 2 days is
Yeah, this Friday is, as the deadline is extended, this Friday is the deadline. So today is one session, tomorrow will be one session, and the next day will be this name is Solve with Us, but this is a kind of activity and open session. The Solve with Us will be on the Thursday, and Friday is the last session.
So in this, we will be you will be clarifying our doubts in the session, sir, or that's the plan?
Yeah, in this session, I will first take your doubts. If you have, please let me know. Please raise your hand to know that, okay, you have doubt. And then if you don't have doubt, then I will do a kind of summary on week 10 for this week 10 and try to how much you'll see how much things we have covered. Okay, so. Okay.
Yes, sir, I have a doubt.
Okay.
It's on activity 10.9, first question.
Okay, just a minute. So, it is not opening. Okay, so this is 19. So what's your doubt?
It's on 10.9, sir. Activity 10.9. 10, then 9th activity.
Okay, so what's your doubt? In which
Yeah,
question?
the first question, see the table is given like AB. So they said, so the circles are giving the cell numbers, right? So
Yeah.
Right.
Yeah.
So let's say the last row, fourth row is saying A1 plus A2 plus A3 and B1, B2, B3. So
Yeah.
B1 plus B2 plus B3 is dependent on A1 plus A2 plus A3.
Yes.
Right.
Yes.
So how actually to interpret? So like if I take the first row, A1 square, what does that mean? A1 power
means whatever the value is here, we don't know what is the value, but yeah, if you take the square, that's the value here for B1. B1
okay,
value is A1 square. B1 value is A1 square.
Okay, whatever comes as a value in cell A1, that will be squared for B1.
Yeah, that would be square. The square value of the A1 will be the B1 value. And as here, this is B1, but and this is B2. The B2 value is B1 minus 10. Sorry, B1. This is B1.
A square
So
minus 10.
yeah, so that's the one thing. A square, A1 square minus 1. But the graph is, you will see it's totally on the direct basis. Like if you see that, like this is the dependency, right? This is the DAG for DAG. This is direct cyclic graph. So if you try to draw the graph, so you will, when you give the circle or when you give the node for like B2, so B2 is depend on, as here is B1. So it will be like this. If you suppose this is suppose this is B1 B2 node, So this is B2 here. So so this is B2. So the directed graph for B2 means inner degree, sorry, inner vertex, sorry, inner edge, one inner
Edge.
edge will be, here is this B1. So it
Yeah.
will be like this.
That's what I thought, sir. But
So it is not meant to, suppose here is A1, so it will be like this. It's depend on here. Yeah, it is, you will say it is kind of like this. So it is like this, but it is not directly meant to say. Okay, if suppose this is A1.
okay, so
This
basically,
is like this.
okay, okay. Yeah, if you go to the graphs, sir, given graphs,
Mhm.
In all four options, B2 don't have any incoming edge.
Yeah. So see that B2 is, it is, if you see B2 is, looks like here is, this is B2. Yeah, okay. So
Yes.
B2 is anywhere you can getting, depend on any cell. No, no, there is
It's
no
B1,
B2 values which is depends on, is there
B1,
any
right,
like,
sir?
huh?
It's dependent on B1, right? B2 is.
Where is that B1? B1 is this one, no? So
Yeah,
B1,
the column A is showing the dependency, right?
column A.
Is it not the?
This is no, where it is dependent. It is written in the form of like A1, B2, B1. It is kind of,
Oh, okay. So, if the cell number is directly given, that means it is it don't have any dependency, is it?
yes, yes, yeah, yeah. That's the mean here.
Oh, okay, okay. Then okay. I was thinking that, okay. So, okay. If it is showing B1 minus 10, then the node,
And
yeah, I mean,
this is A2. No, this is A2,
A2,
not
A2 is dependent on B1
B1
actually.
minus 10. This is B2 is totally
B2
dependent.
is free. Okay, okay,
Yeah.
okay. Sorry, sir. Yeah, yeah. Now I got it. Now I got it. So the last line, like when we read the fourth row, that means B2, B1, B2,
B4.
B3.
B4 is depends on B1, B2, B3. So if you see that B4, which, where is B4? B4 is depend on B1, B2, B3. So this is, yeah, this is
Okay,
right.
okay, okay. Cool. Got it, sir. Got it. I was having trouble understanding. Yeah. Thank you.
Anyone else have? Okay, so let's start the kind of summary because I am looking only 14 participants here, and we need to have to, like, I don't know all of you have watched or gone through the lecture or not. So let me one by one, let's go with, let me open the lecture and let me take the terms from there and we'll explain that. Let's see how long we'll go while summarizing this week. So it's just telling what is graph. Sir, in the first lecture introducing about the graph, what is graph? So as here you can see the relation, like there are some teachers, Kumar, Priya, Aziz, uh, Sela. Okay. So these are the teacher, they taught biology, English, like Sheila can taught maths, Sheila, right. And Aziz only can, can teach biology, Priya only can teach English, Kumar only is one, only the Sheila can teach two things, math and, two courses, two teacher can, like Kumar and Sheila can teach maths. So these are like, these are say, okay, the notes are the teacher and courses are, you can think, the teacher, and who are going to teach is, as here it is shows, like this is a kind of graph meant to say if there are some notes mean to say like in differently for an example, we can take like the airline thing, no? Airline is the best example to say how the graph or what do you mean by the graph. Suppose you have in the first week itself, you have gone through, and in this week also, there are suppose these are two airports and the flight. So if you see the, I don't know how it is, but if you see the map of the airlines route of India, you will see that okay, it will show like this. These kinds of structure you can see, this is this kind of structure you can say this is called in the graph. The single point is, you can say, this is a graph. Even single point is a graph, but this graph contain only one node, or so these are the where the points are, where these are the called edges, and these are the intersection of the lines, you can say, is a vertex. So for this single vertex or node, this is, sorry, single point is called, you can just say this is a single vertex, but there is no edge. So edge mean to say, uh, if you edge mean to say, suppose as you have the, if you see the structure of the airlines route of India, so between two airports, the whatever the way of the aeroplane is showing, that you can think as edge of between two vertices. So edge can be represented as, you can see V1 and V2. Suppose two vertices are V1 and V2. So if you write like in a pairwise, so this is kind of, you can suppose this is V1 and this is V2 without naming as E1. You can directly, it is a convention, or you can say that this is a kind of a representation, that this, if you write the vertices in the pairwise, this represents an edge between these two vertices. That's mean here. So any kind of structure in this kind of structure, you can say is saying to be the graphs, and edges are can be represented like this, or directly it is even, or a capital even, whatever the notation as usually. So the structured to study this kind of structure, the notation is graph can be represented as a capital G, and this is the collection of vertices, and this is the collection of edges. So graph can, you can say that this kind of, the notation is saying to be the graph. This is graph mathematically, you can say, because as you know, it is always not possible to draw always graph, or already the graph of the function itself, the graph of the function, it is not always possible. So always, if it is a vertices and edges, so these are not always possible. Anyhow, you have to go in the theory wise. So such notation is saying to be, let's say this is graph one, say another graph two, which is, this is another graph. So anyhow, we'll try to reach without the this view of structural view, without doing so, we need to algebraic representation of each thing, as in mathematics usually. When you gone through in higher mathematics, you will not always to see a figure or any kind of, this is slowly, so we'll go in deeper as this, will go deeper as a theoretical. When you go more deeper in mathematics, it will totally theoretical. Even if it is like there is a course, algebraic symmetry, and if you see that algebraic symmetry is saying to be the geometry itself, but if you gone through the theories totally on theory, algebra, or this kind of notations only, will see it is not always used to see that the graph or representing some figures are there. So this is about this kind of thing to be, these are the called graph. So more detailed definition, if you see the lecture, that would be good how the graph it is, but kind of rough idea, I mean to say, this kind of representation, this kind of things are saying to be the graph. Graph is nothing but the collection of vertices and edges. These are called the vertices, and between two vertices, if there is a possibility between two vertices, like as this is airport and this is another airport, if there is a airline route in between, then this you can see an edge. So this is the collection. If you collect those all vertices, So V1 representing the collection of vertices and E representing the number of edges. So E is representing the collection of edges. Now there are different types of graph also, like there is undirected graph and directed graph. So best example of a directed graph is undirected. Am I audible?
Yes, yes, sir.
Yes,
You're
sir,
audible.
you are audible, sir.
So directed graph, the best example is the same airline thing. If there is a route like if you see that from Varanasi to Chennai, not Varanasi to Chennai, there is a already one direct flight, but most of the like each day there is very less possibility to find each day as a direct flight from Varanasi to Chennai. So direct flight means as direct means direction itself it says. So if it is, let's say this is, suppose these are the three airports, even V2 and V3. So if you want to reach this V3 from V1, so maybe there is not possible, there is a possibility that there is no route from this airport to this airport. So maybe if you want to go there, then you have to first go here and then it will go to here. So such kind of indication, uh, we'll say that this is a such kind of structure, you can say, where the direction is given in the edge itself. You can say directed graph as here. So if you want to go the airport V3, you have to first go V2 and then from V2 you have to go V3. So such kind of graphs, you can say directed graph. There would be a direction given in the edge itself. And undirected graph is nothing but the graph, but here should be given both side direction. If you think this direction is both side. So such kind of representation. So like this is suppose V1, this is V1, this is V2, and this is V3. So if suppose you can go from this airport to this airport and come back here, so this edge will be look like this. Suppose from here, if it is like this, can go and back to this airport. So for this case, suppose this is the case here, only can go from V2 but not come back to this V2 from V3. It is like this only. So, but here the case is you can go and back to the airport V2. So such kind of like wherever the edges in both way you can go and come back. So these kind of, you can say this kind of graph is undirected graph. Here is, you will say that okay, the direction is given, but now it is, I am removing it, the direction itself. This is V1, V2, because this means that you can go and back to uh, uh, you can go and back to the same airport. That's why without giving the graph, so this kind of, now remove this sign, this structure, this arrow kind of in both side, can remove this, and this is only without the arrow sign, just a line connecting to this vertices is kind of, you can say this is undirected graph. So the next thing is, so if you see that here is again the H is representing V and V prime. These are some, now if you go through the lecture, we'll get that okay, first lecture is just telling about the what is graph. Okay, so there are two terms. There is now the terms are connected and reachable. And the path. There are three terms you can say. Now let me read the. Now I suppose you have there are three terms: path, and reachability. visibility and walk and connect it. There are three different terms. So let's say I'm drawing a graph here. This is V1 vertex, this is V2 vertex, and this is V3, and this is V4. So suppose this is an undirected graph which contains 4 vertices and 2 edges. Okay. So path is a, let me make another. Let's say this is V5 also. Suppose you have a undirected graph, the structure of the graph is look like this. So path, if you say path, is nothing but the sequence of edges or vertices where, so there are two terms, path and walk. There is a difference. Path mean to say you will not repeat, like if you are going with by this way, as the path word itself is given here. If you are going along from vertex V1 to vertex 5, okay. So okay, from V1 to V5. So if you go along this way from V1 to V2 and then V5, okay, and let me modify the mesh structure somewhat. Then we'll see the differences in walk and path. So this is here and V4. Okay, so this is, if you're going like this, this is V1 to V4, and okay, let's say this is, I match this. Okay, so let's suppose you have a graph, this one. Now, if you want to go from V1 to V4, so the path is meant to say you are from V1 to V4, the path is, if you are going like this, from V1 to V2 and then V4, or V1 to V5 and then V4. So this you can, this, if you see that I am not repeating here the vertices even itself. Now suppose I'm going to V4 by this way. From here, from V1 to V2 I went, then back to V3 and then V5 and again V2 and then V4. Like this, I'm going to from V1 to V4. So if you see that I'm again visited the vertex V2 for in the second time here, as I'm going to V1 to V2, then V3, then V5, then V2 again, then V4. So if I'm going like this, by this way, if I'm going, I'm visiting the vertex again V2. So such kind of if you are if you are writing like this, V1 to V2, then V3, then V5, and again V2, and then V5, V4. So if you are collecting this sequence in this way, so this is called walk. And path, if you say that here, the vertex V2 is repeated or visited 2 times. And in the terms of path, the vertex will not repeat here. So if you are going like this, if you are saying this sequence of V1, V2, this is a path. So each vertex will be unique. Unique mean to say only written one time. If you see that this sequence of vertices, this is V1, V2, V3, V5, then V2, and then V4. If you're writing the vertices in this sequence, then this is a representative path because you have repeated here or visited the vertex V2 twice. But if you are writing the sequence of vertices in kind of V1, V2, sorry, V1, V2, V3, where the vertices are not repeating, then it is represent a path. So these two differences in between the path and walk. And reachability means suppose there is another vertex. Suppose this is V6. So if you want to reach from V1 to V6, so if there is a path is available, then you will say this V6 is reachable from V1 if there is no edge that you could reach from V1 to V6, then you will not say that V6 is reachable. And yeah, reachability and connected, there are two terms saying to the same meaning. Connected means the graph is as here, from you can go from any vertex to any vertex. That's the meaning here, connected. As here you cannot go to vertex 6 if you start from uh, uh, any vertex, from any vertex. If you start to reach V6, you cannot. So such kind of graph you can say this is not connected. So this is not connected. Connected means if you are from any vertex to any vertex, you can reach via a path, following a path or a walk. So this is all about in week 1, I think. And this I have started summary. So directed and directed paths. If you see that path are the sequence of connected edges. Reachability is there a path from U to V. So this is in the first lecture. In the second lecture, there are different types of question. We'll see that like this is okay. Now you know what is graph, something you know about the graph. So why we're studying, is there any use or how to convert a question in a graph? So there are different types of problem which will change in the graph questions and easily can solve. Like for example, have sir given a best example to this coloring of, if you have suppose map of India. Okay, suppose you have, don't know how to draw. Suppose this is a map and these are the region, not only India, I don't know which region is this. Let's say this is a graph of a region, and you want to give the different color to suppose you want, if you give this is a red color, then this region will not give to the red color, because if you give red color, then boundary is unable to, will see the clear boundary. Not even how will distinguish the boundary. So you will give the another, let's say this is green color. So if you denote this region, these regions are a vertex. Okay, suppose this region, this is A1, this is A2, this is A3, this is A4. So if you give these regions are you can say vertex, and if you are now, if you want to change such question in the graph, like we want to color the regions with the different colors, such that the two boundaries cannot be have the same, two regions which is adjacent cannot give into the same color. So if you change this graph, so suppose this region is A1 and this region is A2, okay, and let's say this is a boundary. Okay, this line, this is representing the boundary itself. Okay, so if you change, this is, let's say this is A5, this is A6, and this is A7. Okay, so let's say this is A3, A4, A5. So you have to see how the boundaries are connected, like A1 and A2 are as here. So suppose anyhow you change this graph, this region, the coloring of this region to by this way. I don't know, we need not to follow this. I'm not saying this graph is exactly representing, this region is representing this graph. Okay. Suppose this is you change the region coloring of this region to in the graph. Okay, this is A5, let's say this is A2 here already. So now if you want to color this region, let's say you colored this region, then the adjacent boundaries or adjacent region, you cannot give the same color. So this is red here, so these two would be not red. So, and this would be the red. So you just give in the red color here, and you cannot give the red color. Now these two are not red, so let's say you given this one is green. Okay, now you cannot color this one as the green because this is the adjacent region. So now this you can green color. Okay, now if these two are green color, so now you can give this is a yellow. If you say that, if you see that if it is your now 3 colors are needed to decide the boundaries. Like if you suppose this is red, you colored this red, so you can color this one as a red. Okay, now if you color this one is red, you cannot give the red color this one. So but if you said this is a top edge, so you can give this one as a red color. Now you can give this as a green color, so you cannot give this green, but you can give this as a green color. So how many colors needed to color this region? That's the problem. Now if you want to, the question is how many colors is needed to decide or to give the color of this region. So this is called, now you change this problem in the graph, and now the problem is changed in the graph theory, and now this is called the graph coloring problem. Okay, so this is called kind of graph coloring. Now there is another thing. This is map coloring, or see that as here in the video. So the same thing as this is the map of India, and these are the color. If you see that the same, if you suppose this is the edge, sorry, this is a region, so same boundary, same adjacent region will not have the same color, have different colors. So how many colors is needed? So such kind of problem can be changed in the graph, and from there you can solve. Am I audible? Please stop me for not getting.
Yes, sir. You audible.
Okay, so this is called a graph coloring problem. There is one theorem, 4-color theorem, that is mainly on the geographical map. So that is just, sir, it's given the theorem itself. The 4 for the graph derived from geographical map, 4 color is suffices. For you can see that for the India map, you see that only 4 color is needed, map of India. Now there is another type of graph that is called, now if you see the directed, undirected, there is one, you can say, planar graph. So planar, let me open it. Okay. Okay. Planar graph, if you see that, so suppose this is the vertices. If you have, so this is V1, this is V2, this is V3, and this is V4, and these are the edges for the graph. So one more edge, if we start adding the edge, so if you want to connect V1 to V4, I can do this. But if you want to connect V2 and V3, by this way it's not possible. Yeah, you can do by this way, but if you do by this, like this, then these two edges are intersecting. So this is not a planar graph. A planar graph means that graph where the edges will not intersect. Okay. Yeah, you can do by this way. So now our vertices are connected to each other here. So this kind of graph, you can say the planar graph. So usually in this course, we'll study only the planar graph, not see the graph here is not, those are not on, those, like we are not studying, we are not going to study on planar, you can say. Only we'll study the planar graph. The edges will not intersect. So the next thing is, I think the coloring problem have, if you see that the main examples I have given, the uh, scheduling the classroom and
The number of classroom required, no?
yeah, number of classrooms are required when you have different of subjects and having different of timing, like math can teach from 9 to 12 and other subjects can have the classes of the timing while teaching the course. You have some classes of the timing. So how many, say for each course you can give the separate room, but we want to optimize it, like how many rooms are required only to give this, for these courses how many rooms are required. So these problems can be changed in the coloring problem, and give like classing can be given as the age, and timing or subject can be given as a node. Now if you change that problem in the color in the graph and now start the coloring, you cannot give the same color to the which have classing of the timing.
Then, sir, how many classroom required here for na? Because of here the class between math and English, and the one room are when the math class are over, then science are adjust, and also history and English together run. So here to four na.
So here I don't know, sir, how the sir have given the scheduling, because it is totally depend on the timing schedule of the graph. So for example, if you say that the Vex example is itself given in the activity question. So if you see that, let's say an example, this coloring problem. So let me give, this is the same thing as this one.
Yes,
Okay.
sir. Yes, sir.
This problem is totally on this graph curling problem. So suppose this is a, see, if you see that a college conducted an online gaming tournament for one day, and there are 7 games in that tournament, and the time slots for those games are mentioned in the table. This is the game, and this is the game, these are the games, and these are the time slot. Like Fortnite will be played from 10 to 11. So like these are the timing of given for the game for a day from 10 to 1, you can say. Now if you want to draw the graph, so as here you can see the question is, let's games represented the nodes, and there is a edge between 2 nodes if there is a class in between the time. Okay, so we want to draw it as a graph. So how we'll draw this? So let's say
I draw it. I solve.
okay. So how can you tell me that what are the like vertices here? This is, let's say this Fortnite is, can be in the node is F, and Dota.
Fortnite, Dota, Rocket, and Destiny.
Let's say this is Dota and DO, let's say, and this is Rocket, and this is
Rocket, Destiny.
Destiny. So this is, let's say, Destiny DE, and a Battlefield is there, and
Titanfall and Heart.
Titanfall. Okay, Titanfall and
Hearthstone.
Hearthstone. Okay, so Titanfall and Hearthstone. Let's say this one. So this is the games are here. Now, if you see that there is a class in between these two, Fortnite and Dota. So if you see that this is 10 and 11, and this 10 and 30 to 11:30. So you can give an edge in between here. Okay. Now, if you see that Dota and Rocket, what is that? Rocket League. So there is a class. This is 10:30 to 11:30, and this is 10:40 to
Sir,
11:40.
sir, also Fortnite and Rocket also make the connection. Fortnite and
Yeah, so
Rocket.
that's the like one by one you can see that. So Fortnite and Dota is done. Now take the Fortnite, okay, and do which one is classing. So like Fortnite is classing with the Dota and Rocket and
Not,
not
not.
with no one. Okay, so now you can give an there is an edge between here. Now take the Dota and see that how many which one is classing with the Dota. So Dota is 10:30 to 11:30. So Rocket is 10:40. Okay, it is
No.
classing, and this is no one with the Destiny is different. Okay, so with the no one. So there is one edge between the Dota and Rocket. Now if you take the Rocket here, Rocket League. So Rocket League is 10:40 to 11:40. So Destiny with have and no one with that. So only
Destiny only
Destiny.
class.
Now, if you see that Destiny with the Battlefield, and now if you take the now take the Destiny is 11:35 to 12:15. So yeah, Battlefield have with the no one no. So this is the Battlefield you have Destiny with only Battlefield. Now take the Battlefield. This is 11:50 to 12:35. So this have Hearthstone have. This is
Yeah.
Hearthstone have, and this is 12:35. Battle is 12:35. Okay, both have.
Both.
It is classing with the Battle is classing Titan and Hearthstone both. So so this one is here and this one is here. And Hearthstone, and if you see that now take the
Heart,
Hearthstone
Heart
and the Titan have the classing of
plus.
timing. So there is a this one. So this is the graph.
Yes, sir.
Now if you see this, which one is representing? So having two, you can see now see that have two triangle here. So which one have two triangle? So this one no, this one, these three have these two have the triangle. So this is not the structure. If you see that the triangles are not adjacent with one single vertex, have the separate. If you see that this is totally separate, two triangles are separated here. Now the only one have this one. Now the graph would be now if you check one by one, it is actually representing this graph. So it's a different structure is showing this kind of thing. Otherwise, the same graph it is. So this is now, if you see this, now the classing of the timing of your allot. This is the same thing is the allotting the classrooms and the subjects, the teaching timing, the classing of the time. The same, this is the problem here. Now, if you see the next question is totally on the graph coloring. Find the minimum possible number of computers for the tool.
Like same as number of classroom required for the math.
Yeah. So as how many numbers, how many classrooms is needed? You can same here is the how many computers is needed to done this tournament. So now this problem is totally on the graph coloring. Suppose now you given the graph, the color to this vertex is let's say red. So this is red here. So you cannot give the red color to this one and this one. You can give the color to this one is red. And now you cannot give red color to this one. Now you can give the red color to here. Now you cannot give the red color to other vertex. Now take the another green color here. Okay. Now this would be given the green color here. This you cannot give the green color here, but you can give the green color to this vertex, and you cannot give color to this vertex and these two as because these two have classing of the time. They just represent classing of the time. Now if you take the let's say yellow. So yellow is if you give this one, now this will take the yellow color, so you can now give to yellow this one here, the rest. Now between there is no edge between, there is no classing of the time. There is no edge between these two vertices. So how many now colors is needed? Only 3 colors is needed. So now you can answer your question to this one. Only 3 computers is needed to done the tournament. So this is kind of graph coloring problem. Set this is the first activity. This
The last question, sir, in this only how to answer the last question.
in this activity, the same
Yes, sir.
activity.
10.2, sir.
So yeah, the next, still we have to study the independent. So let's first see the what is the independent set, then we'll back to this question. Okay, so now this is graph coloring is done. So now there is one term vertex cover. This is graph.
Vertex cover मतलब sir vertex digit ना?
Yeah. No, vertex cover means, let's see that how the definition itself will see. This is the graph coloring. The next is vertex cover. So the vertex cover is as here an example. Let's see with an example as here the sir is given. You have a hotel. There are many corridors. There are many. Okay, so intersection of the corridor. So there are many corridors, or there are many. You can say, suppose here is the room and here is the one room. So there is one corridor. So like this. So suppose this is another room. So this is the two. Okay, no, this would be not. So in a hotel, if you see that there are many corridors and there are many rooms. So and you want to establish a CCTV camera to in a hotel in an optimized way, like I want to do the minimum number of camera. How many minimum number of camera is needed to cover the all rooms and corridors? You can say the how to cover the all corridors. So you will establish the camera on intersection of the corridors. So that would be nice to cover the all corridors. So suppose let's say so then your problem is now change in the graph theory, like the intersection of the corridors you can represent as a vertex. Okay, so suppose there are two corridors. Let's say this is one and here there are two rooms. So this is one corridor, and suppose here is another room and another room. So there are now these two corridors are intersecting. So this point is now, if you want to change this problem in graph theory, so this intersection point now you can represent the graph. So if you change this problem to in graph theory, so only one vertex is here. Only one vertex. This is the graph for this problem.
Yes.
Okay. So intersections are represented as a node. So suppose like this, now there are the corridors of intersection. Now they represent the nodes. So suppose these are the so that let's say the hotel, now the hotel problem is now change. Anyhow, you change that problem in the graph theory, and now suppose this is the graph. Okay. So this is the graph for the that graph of the representing that problem hotel, and this vertex are representing the intersection as here the corridors, intersection of the corridor, and you want to establish the camera. So how many camera is needed? You want to find that. So suppose you establish here one camera is, now see that only one camera is enough to deal with the all. Like if you establish here one camera, it will see the this corridor also, this portion, the intersection as here. If you establish this here, the camera, that camera can see this one also, this one also, this one also, this one also. So if you establish as here, this is the intersection point of the corridor. So you can if you establish here, so if you establish here the camera, you can see the all vertices. Suppose if you establish the here camera is here, then it can see this one and this one, but it cannot see this one. So you have to establish the another camera is here. So let's say this is V1, V2, V3, and this is V4. So if you establish the camera is here, then the another camera will be established here. So now this generate an independent set. This kind of problem also generate the independent and the minimum vertex cover of the vertex cover. So as you see that how many minimum number of camera is needed for such problem. So vertex cover is a making a V covers all edges from V. So mark smallest subset of V to cover all edges. So that's the problem here. Like, so suppose you have now, let me change it the problem some more. Suppose this is V5, now this is sorry, V4, this is V5, and this is V6. Okay, this is the graph is here. Let's say this is V7. Suppose this is the graph problem. So vertex cover is for this graph is we want to find the subset of vertex, okay, which cover all edges. So we want to find the minimum number of vertices which cover all edges. Okay, suppose now if you choose this vertex, so it can cover this edge only. Okay, but if you choose this vertex, it will cover this edge, and this edge. And we want to find the minimum subset of vertices which cover all maximum possible number of edges. Okay, so if you choose, let's say V4, so it is cover this one, and this one. Now if you choose this vertex, if you choose this one, then only this vertex is covered. This already have covered. So let's choose this one. Now if you choose V1, so it covers this one, and this one also. Okay, and now if you choose any one of now, it is this word, this edge is not covered. So anyone, let's say V2 or V3, any one of the vertex if you choose, then let's say this is V2. To see that this is the 3 vertices is needed to cover the all edges. Now if you see this, you can choose V7, no problem. Now if you choose V7, only cover this one. If you choose V6, it cover this one and this one. Okay, now if you choose V1, it will cover this one, this one. Okay, let's say this is V1, but it still needed some extra vertex. So this is the not minimum because there are 4 vertices and this one contain, this subset is contain 3 vertices. The cardinality here you can say this is the collection of vertices. So minimum number of vertices which cover the all possible edges. You can say that this problem now change in the kind of vertex cover. So these are the types of problem. You can change the problem in graph theory and now you can solve that. Okay, so this is now there is from there now you will see that this is an independent. Now you will see the independent set. What is the independent set? So independent set is the collection of vertices. If you see that this is the subset collection of vertices which that no 2 vertex are connected by an edge. So let me give an example. Let's take this one, the graph itself. This is the vertex cover. Now the vertex cover, if you see that vertex cover is done on the covering the edges. Now if you see the independent set in a graph, independent set, Okay, so now if you let me draw that graph from here itself. So this is undidacted graph first of all. So these are the vertices and these are the edges. These are the vertices. Lines are edges. Now the next one is this. Okay. So now if you want independent set is nothing but the subset of vertices. Let's say this is V1, this is V2, this is V3, this is V4, this is V5, this is V6, this is V7, and this is V8. So these the eight vertices in this graph having 8 vertices. Now we want to find the independent set for this graph. Independent set is nothing but the subset of the vertices. But how we'll choose that vertices? Will that independent set can contain? So there are many. The independent set is can make a graph have more than one independent set. It's depend on how you are choosing the vertices. So suppose I chooses V8. Okay. So independent set or independent set mean to say if we are choosing the vertices such that if you chooses V8, then you cannot choose V7. The two vertices cannot be joined with the NH. You will not choose V1. You cannot choose V7. Sorry, V7 is this one, V7 and V1. You cannot choose V1 and V7. Yeah, you could choose V2 because these are because this V2 is not connected with V8 via NH. So you can choose V2. Okay. Now if you chooses V2, then you cannot choose V3, V1, but yeah, you can choose V4. And yeah, you can choose V4. Now if you chooses V4, then you cannot choose V5. Okay. V1 other vertex, but you can choose V6. Okay. So this is another independent set. If you see that this is a subset of vertices where the edges where if you see that if you take any two vertices will not connected with the NH. If you see that, if you see that V2 is not connected V8, V2 is not connected with V4 or V6. This is an independent. So there are more possibility that like let me say that this is an independent. Let's say I am remove this one. This is an independent set in this graph. But there are some question that the maximum independent set. That means suppose let's say this is V6 I have chosen. Now if you choose any vertex, surely you will get an edge in between them. Let's say now if you choose any one of them, let's say if you choose any vertex now from apart from this vertex, if you choose any vertex, surely you will get an edge in between any one of the vertices. So then you can say this is the maximum independent set. So why such? Now this problem, why this problem is this terms is came. There is an good example. If you say that the dance is going on, or and there are some constant like, so this suppose in our school have some dancing performance is going on. There is one cultural program is going on where the student are used to join a dance. So suppose one student can join two if you want to join two dances, then he cannot, because if he join one dance, okay, and suppose he joined one dance and just beside of that there is another dance he in which he want to join that. So there is a concept that he have to quickly change his dress, and according to that dance, he have to dress up and then perform. So such kind of problem you have to change. So suppose this car. So if you see this problem, this is this problem is totally, if you one by one we see that the constraints, you will see that. So that see that the dances can be represented by a vertex and edges. So edges can be see that the overlaps of dancer. Dancer means two dances. Dancer cannot participate, or if suppose one dance is performed at this timing and another dance is performed at this timing, these two timings are separate, then he can take. But if it is overlap is happening in the same timing, then he cannot. So I have just given in the time also, but if you see that there is no time sir have given, the sir have said the sets of dancers overlap. So here is like, suppose the question, if you see that question is, sir have changed the group. Suppose this is a group of dancer, this is another group of dancers. So two dancer cannot be the same. So in such cases, if there is an overlap is happening, suppose in this group, one person is there in both the groups which perform the different dances, then you can say there is an edge. Okay. So such problem now change in, like, suppose this is, let's say this is group 1, this is group 2, and this is group 3. Group 2 and this is group 3 and this is group 4. Okay. Like this. So suppose there is a person who is taking, he is performing two dances which is in group 2 and group 4. So see that there is no clash, there is no overlap in between the dancer. Suppose no, there are two groups in which there is no person which have the same dance. So the condition is all dances perform in the same timing, the separate. So that's the condition. So suppose in this group, that person, whatever the person contain this group, this is another group which not contain the same person. So there is no age in between that. This says there is a person in between the both group. Okay. So if you want to find so these problems now change in the graph. Now you independent mean this group is totally independent with this group. There is no in between the person which is performing two dances.
Okay,
So like
sir.
if you choose G2, this group G2, V2 or G2, then you can choose now G4 only. So these are the, now I want to find the maximum independent set. So these are such problems. These are different types of problem. There is the next problem is matching. Matching is, we see that how the matching is the same. Matching is based on the good allocation of group. Class projects sir have given. So matching, let me give an example with the example itself. So matching, let me take the graph from here itself. Because you have a graph, let's say this is V1, this is V2, this is V3, this is V4. This is V5, this is V6. This is a graph you have. Now, matching is a subset. If you want to find the matching is a subset of now matching, like I mean to say, if you matching is the subset of the edges here. Independent is subset of vertices, but now here if you see that matching is a subset of edges. If you choose this edge, okay, you cannot choose this edge because there is a common vertex. Okay, here if you see the independent which have the common vertex, you cannot choose that vertex. But if you see the matching have, if you have two common vertices, then you cannot choose that edge. So if you choose this edge, you cannot choose this edge. Okay, you cannot choose this edge. You can choose this edge. Okay, you can choose this edge. Once you choose this edge, you cannot choose this edge, this edge. You can choose only this edge. Okay, so if you are choosing such kind of, so what is the maximum? So maximum means the maximal matching. So how many, like, how will choose that which covers the all? Sorry. So you have to choose a subset of vertex, sorry, edges which cover the all vertices. So if you see that, let me open the find the maximal matching in G. So this is okay. If you suppose it chooses the edge V1 and V6, this is a matching, but I want to see this represent an edge, this edge. Okay. So this is a matching, but I want to choose the maximal matching. Maximal matching means which cover the maximum possible vertex, or mean to say all the vertex. So if you see that, so for this problem, if you see that if you choose this one, then it covers this vertex, this vertex. Okay. Now if you choose this one, this covers this vertex and this vertex. Okay, that's fine. Okay. Okay, and if you choose this one, then it covers this one only. It's still this vertex is remain. Where is that? Okay. No, so that's the best thing. Like I chooses the wrong way. That's why I'm not able to reach the all vertices. See that when I chooses this one, then I cannot choose this one. When I chooses this one, then I cannot choose this one and this one. Okay, but I am unable to choose the whole vertex. So I have to choose such a way that's called a maximal matching. I have to such a way that I will try to cover the whole vertex. Like if it chooses this one, then I cover this vertex, this vertex. Okay. Okay, when I chooses, let's see that here how they. Okay, no, this one. Now see that as here, if sir have chooses this vertex, then this cover this one and this one. If you choose this vertex, then it covers this one and this one. If you choose this edge, then it's cover the whole this two vertex. So see that in a such way, if you chooses the edges, it cover the all vertex. So that is that is called perfect matching. Okay, find the maximal matching, and there is, so this kind of call this if you chooses the edges such that it covers the all vertex, that is called perfect matching. And matching is the maximal matching, mean to say you are able to such how many possible you can choose the edges, that is called the maximal matching. Okay. There is two different, perfect matching and the maximal matching. So for this example, let's say that whatever the sir chooses this one, and this one, this is called perfect matching. These are the some problem. We'll see that. We'll see in an example. So this is called perfect matching. If I choose this one, okay. If I choose this vertex, sorry, this edge, okay. So this is a matching. This is not a, you can say the maximal matching also. This is not a maximal matching because some edges are, some vertex are still remain. So these are something. So perfect matching, maximal matching, so we'll say perfect matching. Here is as here. Find a maximal matching. Is there a perfect matching covering all vertices? So with an example, like it will be a problem, it will with a problem, it will be more clear. So let's see a problem. This the last problem is on the independent set. I think that is on not matching. only on the independent. Okay. So see that a college has sent a sport team for a sport festival in their college. Okay. The team is multi-talented and each individual has the skills to take part in one or more than one sports. However, the same individual cannot be the part of the team for two different sports because of the possible clashing in time. Okay. The graph shown 10.5 is created where the nodes are the events of the ages connect pairs of sports where the teams share the members. Okay, so nodes are the events. Nodes are the events and ages connect pairs of sports where the teams share the member. So ages are the if you see the ages connect the pairs of sports. So ages represent the sports where two members share the two sports share the members. Okay, if the college wants the team members to make to take part in the maximum number of sports. Okay, if the college wants to team members to take part in the maximum number of sports, then choose the set of correct option. The question can be solved by finding the maximum number of independent set. The question can be solved by finding the minimum number of vertex cover. The question can be solved by finding the minimal coloring. The maximum number of sport in which team can be participated is 5. So how will solve this problem? This problem is the problem. You have to first see the problem. If the college wants the team member, okay, so team member he wants, and if you see that nodes are the events and ages represent the connected pairs, ages represent the sports where the team members sharing the members. The college wants the team members to take part the maximum number of sports. So maximum number of sports. See that here the question is the maximum number of sports. So and sports, okay. Maximum number of sports, okay.
Then we solve by maximum in size of independent.
Yeah, then it is solved by the maximum independence. So you want to maximize this. Okay, just a minute. Let's repeat it again. Maximum independent set. Okay, if you do with the maximum independent sets, okay, yeah. So if you do with the maximum independent set, because the graph coloring problem is giving just the how many. If you do with the coloring or minimal coloring, so minimal is the same the minimal. It's if you see the minimum size cover, sorry, size vertex cover. If you do with the vertex cover, the vertex cover is what?
It will give the minimum sports they can share with the team member. Minimal vertex cover.
Vertex cover is kind of graph like minimum number of cameras in it, but here is the problem. Here we want to maximize the number of sports. So this cannot be with the minimum. Okay, the minimal cover is also the minimal. Then the minimum cover is needed, but we want to maximize the number of sport. Maximize the college want to team the members to take the maximum part
sports.
Maximum sports number of sports.
So how will we do that, sir? Nodes represent the different kind of sports.
We have now the independence. So as we did for the independent set is, as here we did for independent set, as see that when we are trying to find the independent set in a graph, so how we will try to find when we chooses V8, okay, we cannot choose V7 because the sports here is in this problem. You see that the sharing members are there. So two members cannot play the same. Two members of the two members or two person cannot play it in two sports. Okay, he cannot play if suppose these are the sports. Okay, and these are the classing of the member. They present the two. This is another sport. So this represent two members are participating in these two sports, this sport and this sport. Okay, so if you chooses a person, if you chooses the maximum number of sport we want, so suppose you use sport, if you chooses this sport, okay, then there are members who have sharing the members, so you cannot choose this sport, you have to choose another sport, so that there will be no clash of the members. So you have to choose some other, like you have to choose, let's say this v2, so there is not sharing of the member. Okay, so like this, if you try to find, then it is the possible, then it's give the maximum number of sports which have, this give the maximum number of sports where the people can take part. If you take this one, then there are the possible member have the same number. So like this, then you have to choose kind of, this problem now can be solved with the independent set. You have to find such an independent sports where the members are not shared.
Yes,
Okay.
Then how the answer is for a maximum number of sports is 6? How we'll get in that question? Answer is for the second, third. Sure.
So now now this problem is now have to find the independent. So choose the independent, maximum number of independent set in this graph. So how we'll choose? Suppose here, let me draw the graph itself here now. This is here. Okay, this is here. This is here. This is here. Okay. This is we have. These are the vertices we have. These are the edges we have. Okay, so we want to find the maximum number of, let's say this is V1, maximum number of vertices we want. Independent set. We have to find the maximum independent set here in this problem now. So if you choose the maximum independent set, if you choose it, let's say this is V1, this is V2, this is V3, V4, V5, V6, V7, V8, and V9. Now, if you choose V1, okay, then you cannot choose V3. So you have to choose V2. So let's say this is V1, you choose this, V2, you choose it. Now, because there is no sharing edge, no, you can choose V2. Now, now you can choose this one or either this one. So if you choose, let's say this V5, okay, let me choose V5. If you chooses V5, then you cannot choose this is V4 here, V4, V6, and V7. Okay, but you can choose now here V8. Okay, if you choose, okay, here is this is V10 and this is V9. But you cannot choose V9. Now you can choose V10. So whatever you chooses here, the vertices, is this maximum independent, or how will know that this is the maximum independent? So choose a different, now if you see that now the different, choose with the different way also. Let's see that how it is. Suppose you chooses V3. Okay. Suppose you have chooses V3. So you cannot choose V5. Okay. So you have to choose V4. Let's say you have chooses V4. Now, when you chooses V4, you cannot choose V5. Okay. Now you can choose but you can choose V6. Okay. Once you chooses V6, you cannot choose V5, V7. You can only choose V8. Now once you chooses V8, then you cannot choose V9. You have to only wait to choose V10. So 1, 2, 3, 4, 5. Here is 1, 2, 3, 4, 5. So if anyhow, if you try to choose only there are only 5 ways. If you see that now, if you choose another way, the maximum maximum like this. If you choose V1 and V2, only V2 is V1 and V2, this is an independent, but we want to try to find the maximum independent. So this is another, this is an independent set, this is an independent set. Okay. There is any other way which have the maximum independent set? To try to choose. If anyhow, if you try to choose it, we will try to minimize. If you choose, let's say, let me choose now directly here. Let's see. V7 and V10. V7. Okay, let's say this is V7. This is V10. Now you cannot choose this one, but you can choose this 3, 4. Okay. So see that this is a kind of independent set, only chooses 4 vertices. Okay, so let's say he's saying V1, V2, V4, V6, V8, and V10. Avoid V6. So 1, 2, 3, 4, 5. Only there. Anyhow, if you are try to find the maximum independent, only the 4 ways. Whatever the if which you try to choose by this way, but if you try to choose by this way, if you choose V10 and then V7, then it covers this one and also this one. It covers this one and also this one. Okay, now only way you have V4. Okay, so V4 once you chooses, then you cannot choose the other thing. So only you have V3 you can choose. Once you chooses V3, then this is, you cannot choose V1 and V2. So if you say this is an independent set, V3, V4, V7 and V10. So if you see that this is only 4 vertices, but we want to try to find the maximum independence. So that's the thing here. So for the now the question is the maximum number of sports in which the team can participate. The maximum number of sports can team participate is 6, 7, 5, 4, whatever the, so maximum number of sports we find now. The maximally we can find the 5. So let's see that how this, what was the answer? I don't know.
6, sir. Answer 6.
So 6 is there. Okay. So is there any other way? Maximum independent. Okay, maybe I am missing something. So is there any other way also to
Sir,
choose?
sir,
They are
after
taking B4, I think,
after-
sir. From B4, they are checking. So then they are getting the maximum, I think, the B4.
Excuse me, sir.
Okay.
Sir, here
Yeah.
I think here the maximum is V2, V1, V4, V7.
Okay, let's see
V8,
that.
V9 and V10.
V1, V2. Okay, V1, V2, then
V4?
V4.
And V7.
Yeah. That time I choose this V5. That's why it's covered the most of the vertices. Now, if you go with the V4, then you can choose now V6. So see that as I chooses and they started with V5 here. So I chooses V1, V2, and V5. So it covers this one, this one, this one. But if you choose V4, then it covers. Now we can choose V6. Okay, V1, V2, V4, V6. Now I can choose this one and this one. So this is V8 and V10. So see that there are many ways to find the independent set, but which one is we can find the maximum independent set? Because here the question is the college wants the team member to take the part in maximum number of sports. Our notes represent the sports. So we want to find such a way that the maximum independent we can find. So yeah, this is one. Yeah, this is a good. Yeah, I just directly choose V5. That's covering the many vertices. But I have to find the maximum independent set. So this is one. See, I have a different see, if I chooses with this way, I have only 4 vertices. When I chooses with this way, this have 5. When I chooses with this way, this have with.
How to check, sir, whether this is the cross-checking is not possible, sir? Is this the maximum? How our answer is right or wrong? How can we check, sir?
So that's the thing here. You have to find best way. You have to go on through with the different because I
every
want to
vertex we have
maximize
to
it.
check.
You have to check. As here I check with the V5. Once I chooses V4, then that gives itself the answer. But I badly I choose V5 and then now reach a conclusion, try to reach a conclusion.
Okay.
Okay.
But the maximum time, maximum is the average of ages, I think. No?
Maximum is the average of ages.
Yeah, maximum time, sir, not each journal, but maximum time, it is average, near average, not average correctly.
If you choose the average, this average is 5, no? But here is we have 6. So not sure. It is not, the average will not give the correct answer.
Oh, yeah. Uh-huh.
Okay, so there are different problems we have. Now
Sir,
let's
I
move
have a doubt. I have doubt in 10.3.
10.3. So let me see what is in the 10.3.
Okay, sir.
First,
Okay.
adjacency matrix, then we'll go on to the 10.3. I think this have the representation of the graph. So there are two types of representation. So
And
adjacency matrix and adjacency
list.
list. There are two ways to represent that.
Yeah.
There is one way is adjacency matrix, and there is
And
another way is adjacency list. Is there adjacency list? So how will so what do you mean by the adjacency matrix? So let's see that. Suppose we have this graph. Okay, from this graph it went this graph. Let's choose this graph, and we have to make a table. Making it. So make a table like this. Let's say table is it will be a square table. Okay, it will be a square table where this is V1, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, and another is 10. So you can now, here is, let's say this is V1, this is V2, V3, V4, V5, V6, V7, V8, V9, and this is V10. Now separately you have to make like this. So how many vertices are there? You can, the cells are in the side of the cell, you can give the vertices number. This is here. This is V1, this is V2, this is V3, this is V4, V5, V6, V7, V8. Okay, the V9. The last one is here. V10. Now, if there is no if there is no edge, then you will give 0. If there is an edge between two vertices, you will give 1. So that's the process. That's the way to find the adjacency matrix. So V1 is will not generally include the edge with the itself. So that's why this here this diagonal thing will always be 0. Okay. Now V1 is have an edge with the V3. So only one will be with the with is V3 and rest all will be 0. These are the entries will be. Okay. So if suppose it is a directed graph, the case is here it is a directed graph. Suppose this is a directed graph. So this says this is a edge from V1 to V3 So you can give here V1 to V3. So V1 says the outer, see, by this way, this is the V1 and V3 have an edge. But when you are at V3, you cannot give 1 here for V1 because the outer, the row wise represent the outer and column represent the inner where it is coming. So V3 cannot, you cannot give 1 here. So for the undirected graph, it will be here 1, but for the directed graph, it will not be here 1. So for suppose this is our case is for undirected graph. So you can give now for V3, there is an edge between V1 and V3. So there will be 1 here and there is an edge between V3 and V2. So here will be 1 and rest all okay. And with the V5 also 1. So this is V4 and this is V5 and rest all will be 0. Let's check for V2. V2 is only edge with the V3 and there is no edge. So this is 0, this is 0, this is 1 here only with V3 and rest all will be 0. This is the way you will fill the entries. So this is called the adjacency matrix. The matrix itself give the edge, which one represent the edge. If you say that this adjacency matrix is the directed graph, then you can fill the, you can find the way, or we can find the graph itself, or if it is indirected graph. So suppose your graph is undirected, then this adjacency matrix will be symmetric with respect to this diagonal. Okay. Symmetric means, you mean to say, if you symmetric means, oh, you all of you not gone through the symmetric matrix. So if you see that with the diagonal, whatever the entry you will find here, you will find the entry with the same one here. That's the mean to say symmetric. So when you come to the matrix part, you will see there transpose thing. There is a transpose of a matrix. So when you take the transpose of matrix, it will not, there is no effect on the entries, and the entries will not change. So that is the one thing. But here for the time, for this maths one, symmetricity you can see in the with respect to the diagonal. So if you find 1 here, there will be 1. So like this, that's the mean to the undirected graph. If it is a directed graph, there is no mean to talking about the symmetricity. So this is called the adjacency matrix, and the entries will be feel like this. There is use of already. So the use of the there is like, see, as in starting itself, I've said, whenever you have a, see, always you will not able to find a way. Always you will not find a way that always you will not find the, like, usually like graph, you have a visual kind of thing, you are able to see that, but this is not a best practice to always see or visualize that. Anyhow, you have to reach a theory so that you can easily solve. So matrix is matrix, the adjacency matrix. Now see, now this adjacent, this graph is now changed in a very concise form, in the matrix form. Now you can do all the performance there. Then now if you see, the theorems will be developed on this matrix easily, because this is a geometric, this is algebraic way to solve the problem with that. Now any graph can be changed in the adjacency matrix. Now you can do the operation, or many theorems, if you see, that will be developed on this adjacency matrix to solve the graph theory problem. So there is another representation of a graph is adjacency list. So adjacency list will contain, here is, if you see that there is n square cells. N square means if you have n vertices, then it have n square cells. But adjacency list is the, if you will collect left side as vertices, and this side is, we'll see that, okay, let's say, suppose this you have V1. So V1 have an edge with the V3 only. So this is only V3. if you take V2 has an edge with only V3. So in this is kind of representation. But if you see V3, if you take V3 an edge, so V3 have an edge with V1, V2, V5. So let me make it a bigger cell. So this is here. So V1, V2, and V5. If you see that V5, so V5 and edge with V3, V4, V6, V7.
V7.
So this is the kind of notation. So this kind of notation, this kind of representation for a graph is called the adjacency list. Both you will see these are the, like when you solve the graph theory problem while when you study with the Python, then there is these matrices will help you to these matrices will help to write a code regarding a graph theory problem to convert a programming problem. That's the thing is here. That's we are studying. So based on these two, there is two algorithm. There is BFS and DFS. We'll discuss on that.
Sir, actually, I have problem here. 10.3
Okay.
activity question last.
Okay.
Yes, sir. This one. There are 5 phases in the graph. So yeah, this one graph.
Mm-hmm.
Yeah.
So
So
how many
according
edges? So this are, so how many edges are here?
here is 5 cross 5, no? So
So sorry, there are 5 vertices.
5 row, 5 column.
Yeah.
So,
So 5.
yeah, but I make a graph, but here it is showing like there are 8 edges, but there are only 7 row and 7 column.
7 row and 7 column.
Yes,
No,
sir.
here is.
But according to my graph, because he generalized, no, there are 5 edges in a graph, so it means that he's saying if the 5 row, 5 column, then it means that 5 edges, no?
Yeah. No,
Then,
no, not 5 edges, 5 vertices. See how many rows are there. See, or how many columns are. These are the number of vertices. No, this 1, 2. So there are 5 vertices or 5 nodes are there.
But here, third option, sir, there are 5 edges in the graph.
So there are 5 edges in the graph. So if you want to find the number of edges, then you have to anyhow try to convert this. Say you have to convert this adjacency metric in the graph. From there you can count the number of edges.
Okay.
If you try to, like, if you want to find the, so if you see that here, then it is a difficulty, no? Like, so V1 have no. So this represent one graph. Sorry, one edge, because V1, V2, and this V1 and V2 and V1. So they present one edge. Okay.
Edge.
This represent one edge. This represent one edge because there is a symmetricity, no? So this
Yes,
represent one edge, and this represent one edge. So this and this represent one edge. This represent one edge. So how many edges are total? 5 edges.
Wait, sir. There are 6 edges, I think. First of all, we take anything number like row, like 1. Then he make the edges with here 0, 1, 0, 0, 1. So so it means that there are 2 edges, no? Of here, look there. Here in row 1 and 1, first row.
1 and 1. Yeah.
First 1 and 1. So here 2, 1 and 1, first row.
First row, and here is.
Yeah, and
this
first
one,
row. This one.
This represent one edge.
And this one and the last one. Last row of.
And this one and this one. This represent one edge. This one and this one, including these two, represent one edge.
Okay. Sorry.
So best way is that you have to convert this matrix in
graph.
the graph.
Into graph, no?
Yeah, then you can easily count that.
Okay. Thank you.
So let's move on to the. So the next is telling about there is one breadth first search and depth first search. So comparing representations are here. So see, there are two. See, if you want to analyze a graph, suppose you have a graph and you want to analyze that graph. So there are two strategies. The first thing is breadth first and another is depth first. There are two strategies. Using that, you will analyze the graph, like there is a reachability, there is a minimum path, the graph is connected or not, the graph is a tree. There are many ways, there are many words like connected, there is a cycle or not. So if you want to analyze these things, so there are two strategies. One is called breadth first search and another is depth first search. There are two strategies to analyze a graph. So let's see the first breadth first search and then we'll see the depth first search. So there is no difference. These search are like, if you see the strategy, so it's look like a very complicated, but it is not a complicated, very easy. Well, when you on the graph itself, it's look like it's look like very easy. Otherwise, it's look like by making a queues, stacks. It's I don't know, for all of you it is easy. It's fine. I don't know, but it's in the graph. When you are in a graph, then it's look like very easy. What do you mean by the breadth first search? Let me make this graph in itself. So suppose this one is, okay, you have this. So see, this is V1, this is V2, this is V3, V4, V6, V5, V6, V7, V8, V9. I think it's a bit different. Okay, no issue. So we have this, suppose we have this graph. So breadth first search, if you want to analyze this graph, so if you see the question, from the question you will see that. So breadth, if you want to search, suppose you want to reach from V1 to V9, okay? Suppose you want to reach V1 to V9. So the question is V9 is reachable from V1 or not? So how will, suppose now there are thousands of vertices, okay? Thousands of vertices. So how will see that the first vertex V1 is the last vertex V1000 is reachable from the first vertex or not? So such type of problem, how we'll do that? So we have to generalize, we have to find a strategy to see that we are able to reach from V1 to V1000 or not. So see, this breadth first search is mostly used for the computational. This is an strategy, no? This is if you see that there could be code will be written in the Python. This is an strategy algorithm. This is an algorithm. Code means algorithm. So this is an this is a way. This is an strategy to this explore or this analyze the graph. So is that V9 is reachable from V1 or not? So how will we start? The breakfast search says there is two terms, visited and explore. So there are two words, visited and explore. Suppose I want to start from the V1, okay? Suppose I started from V1 to explore the graph, okay? So when I started from V1, so I have only one way that I can, from V1, I can only visit the vertex V4. Only visit the vertex V4. Once I reach the vertex V4, now I can explore the vertex V4. How will explore? Means explore mean to say I can see the vertex V3, means visit. This is called visit. I can visit the vertex V2. I can visit the vertex V5. I can visit the vertex V6. So there are four ways, and we can visit the vertex V1, but it's already visited. That's mean to say from V1 I came V4, so it's already visited. So when I started looking from other vertex, so this is called exploring. It's called explore. So from V4 we are started exploring. So when I started exploring, then I can see that okay. So this is the mark, mean to say. When I at V4, I can visit V3, I can visit V2, I can visit V5, I can visit V6. So let's say I visited V6. So now I want to explore. I have already able to visit V6 from V4. So, but I want to now explore the V6. So when I reach to here, okay, from V4 to V6. Now from V4, I can visit V5, I can visit say V7. Okay. Okay. So when I start, let's say I visit V5, let's say I start visiting. So sorry. Now from I can visit V5. So let's say I want to explore V5. Now I can reach from V5 6 to V5. Okay. When I reaches to V5, I able to, when I start visiting which vertex, I can see that from the V5. So I have seen that okay, V4 already visited, V5 already visited, and there is no other vertex to visit. So that means let's back to our V6 and I start again the different whatever we have V7. Okay. So this is the way, this is the now if you see that the strategy will again explain, right? So by making a queue and other things in the if you see in
But
the
sir,
video. Yeah.
hello sir.
Yeah.
This as I'm reading in algorithm book in BFS, we need to move like left, like horizontally. First of all, move left to right. If we got the point vertex, then just write the number like vertex.
Yeah, that's the here Q, that is Q.
Yeah, that's Q, yeah.
So that's the I'm saying, I'm not writing here. That's the mean I'm saying visited. The
Okay,
Q
okay.
is nothing but the collection of visited vertices.
Uh-huh.
Okay. Then I have to start exploring. Once I explored, I remove that.
Mm-hmm.
I will remove that. So the way I'm saying is here that the same thing is like making the queue and one by one doing this. What I am doing here. Okay. So when I reach V6, I can visit vertex B5, I can visit vertex B4, I can visit vertex V7. When I start after visiting that, I can V5C, I can V4C, I can V7C. So I assumed okay, let's move to V5 and I want to explore it. So when I reached to the vertex V5 and started visiting, so I seen that I see that oh, the VFX already visited, V6 already visited. There is no other vertex which I can visit. Then I will back to our V6, okay, and I start again. We have to go with another vertex which one I have not explored. So let's say I see from V6 I can visit V7. So let's explore V7 now. When I explored V7, I started exploring V7. Then I from there I see that okay, V6 I can already visited, so only have V8. So let's now reach to V8 and start exploring it. That's the strategy. Like so, whenever I have a way, I can reach there and start visiting and explore. That's the first visit and then start exploring. If there is no way, just back to our the remaining visited vertex for the particular vertex. So when I
Okay.
have we don't have the vertex now which have already visited and explored or visited already, then we need not to go there. We back to our the previous one where which have remaining the visited vertex, and from there we start exploring it. That's the strategy breakfast search says. So by making the queues, we can see via mouth we cannot remember. That's why we needed a queue. Via mouth, like by speaking this, we cannot always do this. We need a systematic way for making such. So this is the breadth first search. So like let's see now let me the procedure as if now if you see the video lecture, hope you will get that how it is. So what is here now? So suppose I want to start from V1 and I want to check the reachability to V9. Is there any way to find the shortest path, or there is a path or not, or this graph is connected or not? So these properties can be found using the breadth first, or this property can be analyzed with the breadth first search. Breadth first search. So let's say I'm here. Okay, I'm so this is the way as you see in the lecture. Sir, have this strategy is, let's say, this is V1, this is V2, this is V3, this is V4, this is V5, V6, V7, V8, V9. So okay, so this is called, let's say this is visited. So let's say before to start this one, okay, before to start, all are like visited means everyone is now false. Like you can give yeah, because I didn't even start it, so everyone will be false. So once I visited, it will become true. Okay, and this is Q, and this Q is how many vertices I have visited, like from one vertex, how I can see how many vertices I can see. Let's see that how it is. So I started from V1. So from V1, now when I started from V1, it will come true because I visited now it. Okay. So from
Yes, sir.
V1 I started, how many vertices I can visit? Only one, V4. Okay.
Yeah.
I can visit only V4. So you can give V4 here. So that only I can visit V4. Okay. When I visited V4, so there is no other vertex. So just now let's explore V4. So when I reached V4 here, so when I started V4, you can now you can remove V4 here as so this Q is for exploring. Like when I started exploring, you will remove that vertex. So when I say, so from here, when I reach V4, I can visit V2, V3, V5, and V6. So from when so here is now I visited V4, now it will come true here, and this will come from V4, I can visit V2,
V3,
V3,
V5, V5 and
V5, V6, V5 and V6. So I have 4 vertices. I can visit from V4. So let's do for V2. Okay. So now I started exploring V2. So V2 become true here. Okay. So here from here it will be erased. Okay. So from V4 I can only visit V2 I can only visit V4. Okay. So which is already visited. So let's back to our V1. Now you can give, already it is become, now V2 become true here. So anyhow, I have to make it all true. Anyhow means that's the till end of the. So this search, this visit and explore will end when will be no vertex in this queue. So see, V2 become true now because I have explored now. See, there is no V2 and this will become true because I have visited it, and I now there is no V2 in the queue because I have explored now it. Now start explore V3. So because I can visit now, see from V4 I can able to visit V3. So let's visit V4 and start exploring it. So let's erase it now. So when I started exploring, I see that only I can visit V4, which I already visited. Okay. So that's why, so this is, so we have already erased it and now V3 become true. Okay. Now back to, now we have V5. So now V5, so V5 I can visit, now V can become true here. Now started, let's erase it here. So when I erased it here, from V5, I can visit here. I can explore V6 here and V4 here. So now we can give V6 because we have already V4 have visited already. So we will not give to because, sorry, we have already explored it here. So this queue is actually for exploring which one I have not explored. So V4 already we have explored. I will only need to explore V6. So I have just given here V6 and V6 already we have from V4. So either I have just given or no need to give here. Already we have V6 using the V4. So V5 now it is true. Now there is no other vertex. So now let's start V6. So when I started exploring V6, okay. So now need to remove and let's make it true here. And
And
from V6,
V7.
I already V4 is visited, so I have only V7. So you can give V7 because V7 is remain to explore.
Yeah.
Now we come V7 is there is no other. Now let's start V7 to explore V7. So you can remove V7. Now I can visit only this is V8. So I can visit only V8. So still V8 is remain to visit and V6 already visited. So you know need to V6 already explored. So we will not give here V6. Now again, so V7 is now become because I have started exploring it. So it will come true and V8 is in the remain to explore. So this queue is you will give those vertices which we need to explore it one by one, because how I will remember that okay I need to explore V8 now, how I will remember? So you have to put in a queue so that
So, yeah,
it will give the reminder that okay I have remained to visit V8, I have
yeah,
remained to visit V9. Yeah.
like during backtracking, how we know that we explored this one.
How like how so it will come in mind okay I have seen that place, but did I went there and from there I have seen other thing. So to remember this, we will put in a queue. So this queue is actually exploring, and this is for visiting. This
Mhm.
column is for visiting. This is for exploring. So from V8, V7 is done. So now let's V8 is remain to explore. Okay, so when we started exploring it, so we need to erase it. So from V8 we can only visit V9, which have we till now we didn't explore it. So you can give V9, and now we have already now started exploring means visited it. So it will become true. Okay.
So,
No other vertex. V7 is already explored it, so we will not give any here. And V7 is already visited and explored also, so it will come true. Now let's back to V9. So V9 is still remain to explore. So now you can remove it. Okay, we have removed it. Now V9, this is V9 here. So now this become true here. So see that now when I started exploring it, so from here V9 we can only visit V8, which is already visited. So that means you will know there is now you will not there is no vertex here in the queue. You will not give it because already this V8 is explored. Already we have explored V8. So there is no vertex will come in. So from here your strategy will end now. If you see that, so all will come. So there is no vertex remaining to explore in queue. So it will end the strategy now in the algorithm now itself. If you see in the when you write in the code Python, so this is the strategy. So is there any vertex remain to visit? Suppose there is a vertex V10. Okay, this there is no edge. See that if it is here V10. So if it is V10 is here, so it will always be false here. Then you have to start the another. It means you have to means it will be while from V1 we started. No, so from V1 we are unable to reach V10 this tells because this is always false here. When you started breadth first search from V1, we see that we are unable to reach. This tells you that see this queue is now empty. The other things are become true, but V10 is false. Then if you say that suppose you want to reach V10 from V1 to V10, then you will say it is always here is false. This one, then you will say that you cannot reach V10 from V1. That's the meaning here.
okay, sir.
So this is the breadth first search.
So
This
our
is
our BFS is V1, V2, V3, V4, na? V9 tak. V1,
no.
V2,
So
V3.
So see, we started exploring. See, we started this base first to search that we are able to reach V9 or not. For this purpose, we started with first search.
Okay.
And this tells you that, oh yeah, we are able to reach V9 because every vertex V9, even if V9 is true, it is not false. As here for the case I said for V10, from when he started with first search from V10, V1, and we want to check that is this reachable or not. So it is always false. So then you will say this is not V10 is not reachable, but there is no V10. And for the V9 from V9, from V1 to V9, we want to reach.
So
We
sir,
want to check that.
in Python, when we write like this code, then Python give like true and false na answer.
Yeah, suppose the question is in Python, the question is will be write a code to check that the vertex V9 is reachable from V1 or not. So it will return, you write a function or write a code which give true or false. Means if it is true, then you will say it is reachable. If it is false, then you will say it's not reachable. So write a code which give the true or false. That is it reachable or not? That's the question in Python.
Okay.
So if you write this one, if you write, I don't know how the code will be, but if you write this, then yeah, you can say it will return a true. Then you will say yeah, V9 is reachable from V1.
Okay.
So this is the breadth first search. So actually this tells you that if you see that this all vertex is true, that means you will see that this graph is actually connected. If when any one of is false, then it tells you that the graph is not connected. Okay, this breadth first search also give the extra thing. Those of the breadth first search is actually that's the analyzing. If you
Then
want to
sir,
analyze the graph, yeah.
Then sir, what is difference between BFS and DFS?
So
Because
the
I think
DFS is
DFS
also DFS is also to analyze a graph, but it have different strategy. It is a totally on the exploring kind of as you used to search in internet. Okay, suppose when you are Google and you search something, suppose you want to search a book. Okay, so when you are in a search a book, so you given there is a website book fee, let's say book fee. Okay, when you search on Google, so it will give many threads. Okay, from there, suppose you chooses this thread. Okay, and when you started choosing this thread, this give the many threads here. So from there, suppose you chooses this thread. Okay, then anyhow you did not find this book because this book is under this thread, let's say, or this book is under this thread. So what you will do now, you will back to this one. Okay, now start exploring the next one. Okay, again you will reach some, okay, there is no that book find, then you will back to here, then start exploring this one. When you start exploring this thread, then anyhow there is a way, anyhow you reach to that book. This is the internet, no? This is the process
yeah,
to search in. So that
yeah,
is the depth first search. This is the depth first. Sorry.
So we
Yeah,
go we go inside and inside, no?
yeah, depth
Inside and
first. This is the depth, sorry, depth first search. This is the process. This is actually the depth first search. You just check one, you reach one thread and start exploring the inside that. And if you are a dead end, then back to this one and this one and start here. And again, if there is, then again start searching. Okay, if you not you find that okay there is no big, then you start backtrack here, okay, backtrack here, then backtrack here, then next is this one, and start exploring it one by one. If you raise the book, then it is fine. If you not, then start backtracking. This is the depth first search.
Okay, sir. Okay, thank you.
So this is the depth first search and breadth first search are both are for the analyzing the graph, but have two different strategy. Okay, this is all about for today. We'll next session we'll see the, I think, or we'll start from the depth first search and application of breadth first and depth first search, and complexity, DAG, and that topological sorting. We'll see that in the next session.
Okay,
Okay.
sir. Thank you.
So this is all about for this session. I don't know how it is all of you get or not. Is it clear to all of you or not? Okay.
Yes, sir,
Thank you
clear.
so much.
Yes, sir. Yeah.
Okay. So anyone have doubt, please let me know, that we'll just close the session now. Okay. So please watch the lecture now. I hope now we'll get the idea what is vertex, what is edge, what is depth first search, what is depth first search. Now I have given the strategy itself. Now what is depth first search? I have given idea what is the depth first search. This is used to do in the now as a starting. I said I by voice I by voice we are writing this queue and this visited thing. I by mouth I said okay, do like this, do like this. So this is the same thing. Now if you will in a stack, you will form this visited and a stack kind of thing. Stack is nothing but the where we started exploring it. So this the same start is nothing but the same as here a queue, this one, the same stack also a queue. So this is the depth first search. So if you want to write a strategy thing, then you please watch that. Otherwise, we'll quickly jump that depth first search, because this is the way you used to apply the depth first search. This is the strategy in depth. The same. There is nothing changed. This is the depth first search I said. Okay. Thank you so much for joining. Let's see. Now I'm going to end the session. Have a nice day to all of you.